Thank you, and well, no thanks to the organizing committee for not coming to my talk, but thank you to them for having me come here. So it's not a talk by me without, some unsolicited life advice, because that's what I've been doing the last 2 weeks. So while I'm on a soapbox, I just had 3 things that I wanted to say, especially to undergraduates and beginning graduate students. So I'll just tell you a little bit about myself. So I finished Yale in 2010, and I majored in math and philosophy, which was a dual degree. So I didn't have a ton of math. But somehow UC Santa Barbara was very gracious and let me in. So I finished Yale, and then I went to UCSB, and a month before I started at UCSB, my dad died very unexpectedly, and I was just totally crushed. I mean, you're 22 and a parent dies. So I have 3 bullet points. So I really want to emphasize that self-care, and especially mental health resources at schools, are great and they're free. So I went to grief counseling, which was perfect for me, and then I joined a grief poetry group and wrote bad poetry. So that was perfect. So I just, do that. Okay, so number 2, so I was getting better and feeling happier, but still, Santa Barbara is such a wonderful, happy place, and California is so great, and everyone's happy, and it really sucks if you're sad, and you're stop being happy, everyone. So I was having a hard time, and I decided to do this other thing that I think a lot of people don't know about, which is that you can transfer graduate schools, and that's a possibility. You just apply again. So I finished my master's at UC Santa Barbara, and then I went on to UIC. And then, as many of you know, I went on to move to Austin. So the last thing here is the best advice I ever got about graduate school and about life in general, especially once I got to motherhood, is that you can't really look at what other people are doing. You just have to swim in your own lane. So you do you, is sort of that. So that's my unsolicited life advice portion of the talk. And now we'll move on to the research talk. Okay, so I said that we'll be working with the square model of random groups. So sort of maybe I'll put an outline of the talk over here, actually. Okay, so the first thing we'll be talking about is random groups. And I'll say some words about it. Next thing, the second section will be very short because Kasha did it yesterday. So that'll be on cat-0 cube complexes. And the third part will be cubulation / so what. Okay. So first, let's do random groups. Okay, so I will connect this with something that Moon said last week in her lecture. So just to start, I'll say that sort of definition by example, finitely presented groups. So let's do z squared. So what a finite presentation means is you have a list of generators, and that's sort of the first couple things. And then on the second part, you have a list of relators, which tell you how these generators work together to form your group. So z squared is an example of a finitely presented group. And you can make all sorts of finitely presented groups. And so one question that you or Gromov may ask is, if I think about all finitely presented groups, and I kind of pick one at random, will it most likely be hyperbolic? Will it most likely have torsion? Will it most likely have any sort of property of groups that you would want? So Gromov in the 80s sort of made this formal and rigorous by coming up with something called the density model. So today I will be talking about the square model of random groups, hence the title. So the square model of random groups, and when we talk about random groups, we always mean finitely presented groups, which is why I did that first. Okay, so a square model of random groups. So let's say I want to make a random group. Well, how would I do it? So start with a group, and let's say I have a bunch of generators, and then I need to pick a bunch of relators. That's how you make a group. So in the square model of random groups, I'm going to say that all of my relators have length 4. So similar to this guy here, this has length 4. So this is going to be what's happening. So how many possible relators do I have of length 4? Well, or how many possible words, I should say, do I have of length 4? Well, I have 2m choices for my first letter, right? Because I can pick A1, A1 inverse, all the way up to AM and AM inverse. Then for my second letter,
They are reduced, right?
they're what?
Reduced.
Yes, reduced words, absolutely. So what reduced means is that you don't have an A inverse following each other. And that's exactly how we're going to figure out this number. So let me write possible words. Okay, so I have 2m choices for the first letter. For the next letter, I can pick any of those 2m letters except for the inverse of this first one. So if I picked an A1, I better not pick an A1 inverse here. So that means I have 2m minus 1 choices for my second letter. Similarly, I have 2m minus 1 choices for my third and for my fourth letters. So I have, this is sort of the total number of words that I could possibly put into this relator set. So now the question is, well, OK, how many words do I want?
So don't you want to like cyclically reduce in the square model?
Just for,
Okay.
we're just going to do this one. That's harder. So I'm going to pick some of these. And what am I going to do? So I'll say I'm going to fix something called a density parameter. And this also comes up, I should have said this a second ago. There are a whole bunch of models of random groups. Any model you take will be fundamentally flawed. Like this one's weird because all relators are length 4. And so sort of all of them are weird in different ways. But they're useful. So that's why we're going to stick with them. So we'll pick a density parameter. And that's going to be between 0. That's not right. 0 and 1. OK. So how many relators am I going to choose? Well, I'm going to take, you may have noticed that this is something on the order of m to the 4th, right? There's some numbers in there, but it's around m to the 4th. So I'm going to choose m to the 4 times d, and maybe just put a little, make it an actual real number of relators to throw in here. So when I make my group, I will have m relators, or m generators, and then I will pick this number of relators with uniform probability from this huge set. And that'll be my random group. So we say that a random group in the square model has a property, like whatever property we want, right? Like earlier I said hyperbolic or torsion-free. So we say it has the property P if sort of the number of groups with that property over the total number of groups, right? Because this is still a finite number if I have some fixed m, right? So the total such number of groups approaches 1 as the number of generators goes to infinity. Yeah, Maddie.
Okay, I'm sort of confused because if you have, how do you know that you can like choose which one of them to be equal to identity like independently? Because what if you had one and it's inverse in there and you chose one of those?
Right. So this can happen. Yeah. No, that's totally a good point. So the program next year for the Women in Math program is random groups, and it sort of deals with these. But like bad things happen with random groups, and you really have to deal with a lot of sort of probabilistic arguments when you're doing it, because these sorts of things can happen. So for example, like some of the very first results that you get with this sort of square model. I need to write down someone's name. And I don't know how to say it, but you'll see why. OK, how do you say it? Right, you just say it like that. Obviously, Odrigucht. So this is a person who defined the square model of random groups. I just want to say that just last year.
I guess the probability of choosing the same thing twice goes to 0.
Right, because there's just a whole lot of these words. And you're picking them with uniform probability. So similarly, choosing something and its inverse, not very likely, but can happen.
So is D fixed, and then you take
Yes.
it? Okay.
Yeah, oh gosh, I didn't even write it down. Thank you. So random group in the square model, that's actually incredibly important. This is sort of a unhelpful statement unless you include that at density D. I'll just put it over here. Okay, so some of the sort of first things that are kind of interesting is that if I pick too many words, and not over half of them, but over the square root of all possible ones, then almost certainly my group is trivial, or just because of the thing, or z mod 4z. It just like gets stuck and doesn't cancel out everything. But almost surely you get trivial if you pick too many relators. And if I pick sort of less than that, almost surely my group is hyperbolic. And so Moon also defined hyperbolic, but we can just think of it as sort of like free groups in some way. Tree-like is the Cayley graph, and I'll talk about the Cayley graph in a bit. And so the way that this model says that something is hyperbolic is it shows that, in fact, I'll talk about the Cayley graph right now. Shows that the Cayley graph satisfies something called a linear isoparametric inequality. And Moon literally said the word isoparametric inequality on the last day of her course. So what is an isoparametric inequality? So I will just draw a picture and explain. So I have z squared there. And if we remember the Cayley graph of a group, what I do is I draw a vertex for every element in the group. And so we kind of know what z squared looks like, right? It's this lattice of points. And then I draw lines or edges between those points, if you can get from one to another with the generator. Okay, so this is the Cayley graph of z squared. With sort of the standard generators. Okay, so an isoparametric inequality, vaguely, tells me that whenever I make a loop of any kind, the ratio of the length of the outside of that loop, so I'll just call it boundary of the thing, over this is going to satisfy something linear. So I'll write down what it actually is for random groups. It's 1 minus 2d minus epsilon times 4. So maybe this will be easier to see why I call it linear. That's why it's linear. It looks linear. So this is a linear isoparametric inequality. And so there's a theorem, or really this is sort of one of the first definitions of having a hyperbolic group, says that its Cayley graph satisfies a linear isoparametric inequality. And so something that you might notice about z squared is that it is not hyperbolic. And kind of a reason is because this ratio between the outside of a loop and sort of the number of squares, size of d here is the number of squares inside, that ratio is more quadratic, right? Because when we think about Euclidean space, area changes quadratically with respect to linear things changing. And you can sort of see that in this picture. Somehow the number of cells inside is changing much faster than the number of length outside. So
D there is the density?
Yes, this is D is the density. So this is due to Olivier. It's, yeah, for any epsilon. It's used elsewhere, but we'll just lose it. We don't need it. Let's just do that. So the point is that it satisfies a linear isoparametric inequality. And not only that, so that tells you it's hyperbolic, but this also gives you a way to work with, that's the title of the talk, work with this model of random groups, because you kind of know what the Cayley graph can and can't look like. Like it can't have, you can't draw some crazy diagram that doesn't satisfy this. Right? So if you know this, you know the density, then you'll know sort of what can and can't happen. Okay, so that's Cayley graphs and random groups. Okay, so I'm going to quickly review sort of some of the things that happened in Kasia's talk. And since she gave a talk, I won't review it too long, so let's see if I can draw some crazy picture. I'm just trying to draw a picture of a. So a cube complex is what happens when you glue together a whole bunch of cubes. So here I am gluing together cubes, and look, 1, 2, 3, 4. You can glue them together in weird ways like this. And maybe I'll add another one. Let's see if this works. Okay, 1, 2. Oh, no, that shouldn't go there. Let's put that there. Great. Okay, so this is a cube complex, and this crazy cube is still a cube. It's got 4 sides. Okay, so maybe we should have mentioned this more strongly. Cube complexes aren't necessarily embedded in Rn. So even though each length of these sides should be 1, it might not make sense in sort of our world, and that's A-okay. Okay, so that's a cube complex. You glue together cubes, and we say it's cat 0 if your cube complex is simply connected, so there's no loops in it, and your links of vertices do not contain either empty triangles or these 2 dots that kind of are like this, or a 1 dot that has a loop around it. So just a picture. Here's a vertex. So the link is it's a complex that happens when you sort of intersect a sphere of length 1/3 centered at that point with your thing. So here is an empty triangle, right? So because there's no sort of cube filling it in, and this is bad, right? I don't want that. And the reason is because if you have an empty triangle, that implies something about positive curvature. Somehow you're more like a sphere, and we don't like that. We don't like positive curvature. We want non-positively curved things. So that's sort of what a link is. And hopefully I did that correctly to say sort of, why do we like cat 0 cube complexes, or why do we like cube complexes? Because we can cut them in half. And mathematicians like cutting things in half and looking at the 2 halves and figuring out what's going on with those 2 halves. So, but if you don't have a cat 0 cube complex, you might not be able to cut something in half. So let's see. I don't think I did it right, but okay. Well, we'll see. So here I am trying to draw sort of cutting something in half. So I just drew the line that cuts that square in half. And then I'm going to continue it through my cube complex. So it goes there, and then it goes there. All right, so it's cutting. I'm just cutting each square in half. And now I'm up here. I've kind of gone around, and I'm going to cut this cube in half. So that means I will make this sort of square that's cutting this cube in half. And I'm going through here. I'm cutting through here. So this is bad, right? Because when you cut things in half, you don't want to keep cutting and then run back into where you've cut. And so the reason why we like cat 0 cube complexes, and a more general thing is called a special cube complex, is because this thing that I just drew doesn't happen. So this is a non-example of a cat 0 cube complex. And what's nice about cat 0 cube complexes, again, is when you try to cut these hypergraphs that sort of cut through things, then they don't run into each other. So there's that. Okay. That is Kasha teaching me about Morse functions. So that's 2. Okay, so that's as long as that section is. But maybe I should ask if there are any questions. It was very helpful if you went to Kasha's talk, but if you didn't, it's fine.
I have a question. Can you, like, if you have, I sort of, maybe I remember it wrong from Kasha's talk, but like if you have a link like that, can you not just like fill it in with a cube of a higher dimension, and then shouldn't you somehow be able to make it cat 0, in which case I don't see how this picture goes away?
Yeah, so there is something called a cat 0 completion of a cube complex, and this is sort of what Nassim is saying. You just sort of fill in cubes so that your thing becomes cat 0. And if I filled in a cube here, then these 2 would not they'd be somehow different from each other if I filled in a cube here. So it's like if I have 2 cubes sort of next to each other and I cut them, it'll be okay. It's possible that it's not this length, the vertex, that's the problem, but this one. Yeah, I might have just circled the wrong one. But yeah, these are the obstructions. But yes, generally you can kind of fill in cube complexes and make them cat zero, which is great because that brings us to our next section, which is how do I build a cat zero cube complex? So this construction is due to Sagiv, and this was part of his thesis in 1999. And he did it, again, for sort of a more general case, rather than sort of this. I said cat zero is what we want, but really special is what we want. Here, we're going to use these Cayley graphs, but Sagiv did them for something more general, codimension 1 subspaces, and he called them wall spaces, but forget about it. I just wanted to say that. But Wise, at some point, decided, well, why don't we use this Sagiv construction on Cayley complexes, on Cayley graphs? And this is great because that gives me a way for my group to act on a cube complex. So we're just going to go through sort of proof by example again. So I will take Z6, or Z mod 6Z. So let's draw the Cayley graph. It's great. There are 6 elements, and I am going to generate it by 1. So that's my Cayley graph. And I might as well, just for completion's sake, label the vertices by the group element. There we go. This is Z mod 6Z for now. OK, so how would I make a cube complex out of this that Z mod 6 is going to act on? So first, I'll draw sort of in the idea of that, I'm going to draw these walls. So I'm going to cut my Cayley graph, cut each relator into 2. And so this really only works with even length relators, but luckily, since I'm in the square model of random groups, my relators are even length. Okay, so there's 1. And then I'm just going to add all of the things to kind of cut relator in half. OK, so I have these nice pictures. And now I'm going to build my cube complex X. OK, so vertices of X are going to be a choice of orientation on these sort of hypergraphs, I believe is the term. So choice of orientation of hypergraph. And what that means is that for each hypergraph, I'm going to pick, do I point that way or do I point that way? Yeah.
What do you mean by hypergraph? You mean cutting?
Yeah, these colors that cut these Cayley graphs. So I'm saying hypergraph a little bit reluctantly because the nomenclature is not quite down. I have heard them called Wise tracks after Danny Wise, which I think is extremely cute, but I don't know if anyone actually says that. And then the paper that I'm sort of working on and looking at uses hypergraphs because it's sort of a Cayley graph, so somehow there's the graph word in there. OK, so choice of orientation of hypergraphs. So let's do an example. Oh, those colors are the same. I'm sorry. I thought they were different. OK, we'll do this one instead. OK. So let's say if I pick sort of red pointing this way, blue pointing this way, and yellow pointing this way. Right? If I pick those 3, that gives me a vertex. Okay. And then if I pick, say, if I pick the same red and yellow, but I pick blue pointing that way, that'll give me a second vertex, right? Because it's a different choice of these orientations. So you take all of the hypergraphs in your huge Cayley graph, and you decide, am I going to point this way or that way for all of them? And maybe I'll add a note here that the only thing you can't do is if you have 2 parallel hypergraphs, you can't point them away from each other. That's it. That's the only rule. Don't do that. So back here, let's say I'm just going to label this point by 1, right? Because it somehow corresponds to this vertex that's being pointed at, right? I'm picking yellow, blue, and red all pointing to this vertex, so I'm going to label it as 1. And then it's connecting over to 2, so I'm going to color that edge by the same color as the hypergraph. Right? So vertices are choices of orientation, and then edges are in between 2 vertices if you switch exactly 1 orientation. I should note that Kasia mentioned this sort of at the end of the first section of her talk. She said the Sagiv cubulation is so helpful and everyone should know it, but I'm not going to explain it. And then I'm explaining it, so now you know it. So that's great. OK, so 1, 2. And so let's see. So I've got red pointing at 2, yellow pointing at 2, blue pointing at 2. What if, say, I cross yellow, right? So if I have yellow pointing down, and I have red and blue pointing towards 2 this way, well, it's not pointing at a region anymore that's labeled by a vertex, or by a group element, but it is pointing at something, and something that satisfies this. So it's still going to be a vertex in my cube complex, but it won't be labeled by sort of a group element. So maybe I'll just label it by like a V. Okay, and this is where the cube part of the cube complex comes in. Let's cross yellow from 1. Okay, so yellow from 1 gives me 0. Now if I point at 0, so yellow, and then red and blue, and I cross blue. Okay, you may believe this. You may just have to figure it out on your own. This is, in fact, that same region that isn't pointed at, that isn't labeled as here. So this does, in fact, make a cube. And by cube, we mean sort of cube in any dimension when we say cube complex. And similarly, I can kind of build my whole thing, and it turns out I end up getting a 3 cube. Okay, so I can label it. Let's see, if I cross red, I get a 3. If I cross yellow, I will get a 4 down here. If I cross blue, I'll get a 5. And 5 cross red gives me back to 0. That's great. Okay. So maybe there's just like an observation here, is that if I have n pairwise intersecting hypergraphs sort of in my Cayley complex, then that will form an n cube in my cube complex. And this is exactly where cubes come from in the cube complexes, from these hypergraphs pairwise intersecting. Okay, so
When can you have parallel hypergraphs?
Here's an example. There's one, and it's parallel to this one. Yeah, so in Z squared, I can make these hypergraphs. Maybe there's too many colors here. Yeah, so, and exercise, if you don't feel like listening to the rest of the talk, which is your prerogative, but you're missing out. Exercise, if you do this construction, sort of choice of orientations and connect things, if you switch with Z squared, you get a copy of Z squared back. Right? And in fact, if you do it with any cat-0 cube complex, then you should get that same cat-0 cube complex back. And you can kind of see it with this duality thing. OK, so now we've made a cat-0 cube complex, but we haven't quite cubulated. So you might remember, and I'm just going to, no, I'll write it down. OK, so what is cubulation? That means that you find a cat-0 cube complex. So I keep using X for my cat-0 cube complex. So you find a group G that acts on this cat-0 cube complex, and it is co-compactly, properly, and by isometries. OK, so I'm just not going to deal with those words. It acts nicely somehow. And so let's just try to see what that action is in this case. Right, so I have Z mod 6Z, and I want to know, if you give me an element, what does it do to this actual cube complex? Well, I can kind of see it. Like what, for instance, does the element 2 do? Well, in the Cayley graph, 2 sends 0 goes to 2, 2 goes to 4, 4 goes to 0, and 1 goes to 3, 3 goes to 5, and 5 goes to 1. Right, like this is sort of 1 plus 2 is 3 sort of thing. So if I go back over here, what happens? So 1 gets sent to 3, gets sent to 5, and those sort of cycle each other. And 2, 4, and 0 cycle through each other. So what does 2 do? It rotates the cube complex, this cube, along this axis between V and X. So that's really the only point of me labeling V and X. So similarly, each group element is going to do something different to the cube. But so that's sort of where this action comes from. So this is great. I mean, Sagiev's cubulation is amazing, and we love it, and everyone does it. And maybe I should say sort of why we do that. OK, yeah, great. We are on to section. Oh, yeah. to the so what part of cubulation. So really, like, why would we do this? It's like, oh, it's so great to have this like cat zero cube complex on which I act nicely, but why? And so I'm going to tell a story, the story of geometric group theory. So in 1982, Gromov was like, hey world, let's try to understand these things called three manifolds. I have an idea. I will write down 23 questions, world, and you answer them, and then we will understand these things called three manifolds. Thurston. Did I say Gromov? I'm sorry. I'm sorry. Thurston, yes. And I also said 23. It's 24, but I like saying 23, and you'll see why in a second. So by 2012, all but 4 of these had been answered, right? And somehow there was this one last thing. All 4 of them were sort of equivalent to this thing called the virtual Hawking conjecture. And people, like, this is now a 30-year-old problem. People have been working on it for a really long time. And so... Well, I guess not compared to Gauss's circle problem. All right, so I know. So here's a theorem. So if I start with a hyperbolic group, and I didn't really define it, I just said, well, linear isometric inequality. There you go, you have a definition of hyperbolic group. So if I have a hyperbolic group, and it acts on, let's stick with cat zero cube complex, acts nicely, right, using all of those things over there, then G is, I sort of said the word special earlier, so I'm just going to write it down here. But instead of really caring about it, I'll just sort of say what it means. So, for instance, G is now isomorphic to a subgroup of a right-angled Artin group, which Kasha mentioned yesterday, or quasi-convex, so certain types of subgroups. I'll write some subgroups, but they're quasi-convex subgroups, are separable. And so this is something that Priyam said in her talk, but maybe instead of giving a definition of that, I'll just say that it means they're residually finite. Okay, so very quickly I'll sort of say what that is and say people care about it. Maybe I'll just say people care about it. Who cares what residually finite means? Other people care about it. And so this theorem is by Ian Agel, and this theorem answered all 4 of those questions. It sort of finished it off with a whole lot of work by other people, including people in the audience. But like, he made $3 million from it. So whenever I asked my advisor, like, what should I tell people? Why this is important? It's like, $3 million. That's why it's important. So it answered sort of the last 4 questions in one fell swoop. And so I like saying 23 instead of 24 because there's one icky little question left over, and Alan Reed called me out on it last time I gave this talk. It has to do with rational growth, which, you know, again, Moon sort of talked about, but we'll just say it's not that important. Like, who cares? You know, a lot of people care. Many people are working on that problem. So this is sort of why we care about cubulation, because this is saying if I have a cubulated hyperbolic group, then it has this property that does all of these nice things. Maybe I'll draw a cartoon for residually finite. So cartoon for what residually finite means, you give me a group element.
G.
Thank you. All right. And what residually finite means is that I can find a compact, I can find a finite index subgroup that doesn't include G. And I might as well, since I'm here, say, I said quasi-convex subgroups are separable. Subgroup separability means that if you give me a group element and some quasi-convex subgroup, I can find this finite index subgroup that contains it and separates it from G. That's what separable means. People care about it. You don't have to care about it, but again, it came up in Priyam's talk. So, okay, so in the last couple of minutes, I'll talk a little bit about what I'm doing. So you may have guessed, based on sort of the flow of things, that I'd like to cubulate random groups. And that guess would be correct. So thus far, sort of the work in it is that Olivier and Wise, right, that same Wise, he's all over the place, have so far cubulated random groups in the density model, which I haven't explained, but it's so cubulated up to density 1/6 in some other model. But they showed that maybe you could do something like cubulation up to density 1/5. That Zagiev's construction might work up to density 1/5. And after that, everything is horrible. After that, in this model, you only have one hypergraph. So it super intersects itself, and it's super not, everything is bad. So, right, because we needed to have sort of two different sides when we did that. So they cubulated up to 1/6. So my ultimate goal is to show that we can push this up to 1/5. And sort of my goal for the moment is to take this square model thing and do let's say a partial cubulation up to 1/3. And sort of the way I'm doing it is this linear isoparametric inequality, like I said, and that kind of gives you, oh, did I bring it? I don't have it. It gives you conditions on what the Cayley graph can look like, or the Cayley complex can look like. And in particular, it tells you, well, if I want, say, 3 hypergraphs that are intersecting all together, so I can make one of these 3 cubes, like the resulting complex inside the Cayley complex can only look a certain number of ways. In fact, there's only 3 ways that I can make a 3 cube inside my Cayley complex, or inside my cat 0 cube complex. And so I'm using this linear isoparametric inequality to sort of put limits on what the Cayley graph can look like, which gives me sort of limits on what the cat 0 cube complex can look like, which gives me limits on what the action can do. And yes, but that takes work. Yeah, that's because of this linear, non-planar version of the linear isoparametric inequality. Tells you eventually that there can't be any 4 cubes. Yeah. So let's see, where was I? Square model, density less than 1/3. Yeah, that's the goal. And I guess that's it. So thanks so much. Any